Okay, good afternoon, everyone. Welcome to Aries Astrophysical Seminar Series. So we are delighted to have Professor S.K. Saha with us today, who will be talking on genesis of optical interferometry. So first of all, I would request our director, Aries, to introduce the speaker.
Thank you, Vaibhav. So as the title says, there is a genesis, or you mentioned the word genesis. So Professor Saha, we call him Shopunda, because when I was a student, he was a faculty. I took his classes and you also took his classes. So I think it's a very nice occasion to see the Guru Shishya Parampara. So yeah, Professor Saha did his PhD from radio physics department. Again, that department was Calcutta University. It was next to my master's, a department in the same campus. And then he did a postdoc period in France. And in fact, I remember you had a Nature paper during your postdoc tenure. And then he joined IAA at Kodaikanal Observatory. So we were just discussing, because Kodaikanal is completing its 125 year celebration, and the meeting is scheduled on 1st of April. So some of us, I was also posted at Kodaikanal in my first job. So we have been asked to come there. So I think very nice to have you here. So his expertise is on optical instrumentation, more specifically on interferometry. In fact, when I started my PhD early 90s, interferometric technique was in infancy. And in fact, he had his expertise in specular reconstruction. I remember image processing, there used to be something called lucky imaging. People were, because particularly for solar observations, you have lots of images, but when you look at individual images, they're not sharp enough. So the thing was, people were trying to, of course, this is much before the adaptive optics came in. So a lot of image processing things were happening, and some in form of optics as well started happening. So he built a Speckle actually for convolution. This was, I think, early 90s again. So I think a lot of legacy issues. So thank you for coming. He was just, in this area. Then I was visiting the other temple, which is famous nowadays after Kohli's visit. So, so I just told Shapadavari to come and visit us and give us a seminar. And there's a large interest here on instrumentation, particularly in optics. So thank you for coming in, and stage is yours.
Thank you. I differ with your last sentence that after Kohli's business, I'm not fascinated about temple. My temple is library and instrument. And somebody was interested. I said, okay, I'll also join. Okay. Anyway, as you mentioned that my PhD was with Professor Shen, who was a student of M. Kadas Gupta. I'll come to this place talking about him. So background is radio physics, joined in Kodaikanal, got transferred to Bangalore. J.C. Bhattacharya, the then director of the institute. He was also a student of radio physics, but he loves doing experiments. So he doesn't like the ready-made instrument, get the data, put the spectroscopy, and analyze. He said, no, something should be built new. The new, we had one professor sarcastically, he said, go to Himalaya, meditate, and get the new idea, how to go about it. So he called me one day in his office. He said, you could develop this. Then I said, with my radio physics background, and optical wavelength, much shorter. I said, what's the problem? You do it. Now, those days in 80s, midnight 80s, these particular topics, people are publishing paper, but no article is mentioning that what is the physics behind it. How do you do it? It's a completely different subject. The optical imaging, that was Speckle. So I started searching IISc, IIA, RRI, no books, no articles here and there. So the best way to attack the problem is do experiment and learn. So this name I gave to start how the interferometry started from Young's days onwards. Have you heard of? Can you put, okay. Young, 1801. What he did is, he just allowed sunlight to come and fall on a mask, the two pinholes he has put, and then he saw bands on the screen, white and dark. And he analyzed that light plus light, it is 4I, and light plus light, it is 0. The fringes you can see, those are in phase, they are, is it coming? Oh, the front one, oh, okay, okay. You see, the peak is very sharp. The intensity is high. The other one, slowly it is coming down. The first order, second order, everything. So now go to the Fizeau. He suggested that if you put a mask on the telescope, and you will be able to resolve some of the stars. So those days, Stephen, he used 80 centimeter focal telescope. He had put a mask that is 65 centimeters, he could go maximum. And he declared that fringes are very sharp. Nothing is getting masked or anything. So you cannot resolve any stars. He tried with Sirius. So what we did is, we also did the same thing. Remember, in those days, there was no camera. You could observe visually. And my first experiment with 14-inch telescope, we have the similar one we had in Kavalud. I put a mask and we made 10 centimeter holes. And then we saw the fringes. At that time, initial experiment, there was no setup like this. And we saw beautiful fringes. And the same J.C. Bhattacharya was present at that time. He said, I have never seen such a fringe in my life. Why can't you take a photograph? And nobody knew how to take the photograph. So we started doing some R&D, and then we made a setup like this. What we did is that we have put a Barlow lens here. It's a bifocal lens. Here's a Barlow lens. So it magnifies. And then it is f13 beam. We made it f65. And we put a broadband filter. And then we put a movie camera there. We had one 16 mm movie camera. It was lying in the workshop, stores. Got it out. For getting the film, I sent somebody to Madras. 16 mm film came. And then we put that film. The fringes, started analyzing. And we were successful to get the fringes. Then we put another one there. Third one. There we saw two of them are coming and merging. Third one is coming very close, but not merging. Because if you merge, then you will get bispectrum type of this one, fringes. So we started analyzing why. Series of frames, hundreds of frames we started analyzing with the projector. Very close it is coming, it's not doing it. Then we started analyzing and found that the speed is fine, exposure also is fine, but the speed 16 frames per second is not enough. You require minimum 50. Then one of them may come and merge. So it was worrying me for a long time. The same year, Baldwin Group and Hanif Group, they used 2.2 meter telescope in Hawaii, and they used CCD. And I believe more than 1,000 frames. Out of 1,000 frames, they only one picture had fringes of 3 aperture fringes. So they published in Nature and we published in current size. That is the difference. Technology difference. They use CCD. They use 2.2-meter telescope. They used place like Hawaii. We used convolute, 1-meter telescope with a movie camera. So that is the difference. Same year. And then, anyway, go back that the Michelson, he wanted to do interferometry. So first he tried with a 100 centimeter telescope, put in the mask, and then he resolved Betelgeuse. Later on, he used stellar interferometer 1920. There are 4 mirrors, 2 mirrors in the outer edge and 2 are inside. That M2, M3 are inside. There's a girder. The 100 centimeter telescope is here. No, 100 inch telescope, sorry, 2.5 meter. 2.5 meter, it reflects, and he was observing fringes somewhere here. Next one I can show you. No, that image is not here. We removed it yesterday, no, that one. The number of slides are getting more. So he could resolve Betelgeuse 1921, published it with fees. Then he declared, again, he observed, he did not record it. We were the only guy who could record it with movie camera. When I told this to Dainty, he was surprised. He said, Michelson could not do it. I said, he might not have thought that it can record. And we did it. So they just observed and then made this one. Later on, he left fees. He continued to do this experiment, but and then they made a 50-meter baseline, this kind of structure, and he could get another 6 stars they could resolve. That is the end of Michelson stellar interferometry, 1930. Then Second World War came, nobody progressed. Then the intensity interferometry came. The interferometry, M. Gupta joined with Henry Brown and Jennison for radio wavelength. It is something like this. You put one antenna somewhere here, the other antenna about 4 kilometers away, and then we get the detector, put the detector, squallow detector, get the data. In the lab, you correlate, and then you get that is how Cygnus A and Cassiopeia, they could resolve. And of course, M. Gupta, after his PhD, came back. Jennison left. He went for a third aperture, and the phase closer technique was developed by him. And when he Brown, he thought, why not we try with optics? So he and Twist, they did some kind of because it's a second order correlation. The second order correlation and problem is the photon, number of photons will be very less. So this is the structure, but the effect was used in a weak correlation, because second order correlation. And then he made it success. This was the laboratory experiment with a PMT. One of them is moving to have the path length compensation. There's a correlator. And once it is successful in the lab, he found out some second order rejected searchlight. So he has put 2 of them with 20-meter baseline, and he could resolve Sirius. But then it was in the Manchester Jodel Bank. So the scintillation was creating problem. After getting its success, he got a fund, came to Sydney, Narrabri. He has made, there are 6.6 meter telescope size, 6.5 meter. It's a mosaic of 252 hexagonal shape mirrors. And he made a circular railway track. Here one, here. And up to 2.5 magnitude, they could resolve 32 stars. And they could measure even the orbit of Spica. but the accuracy was so beautiful. Even today, people are taking as a standard result. Then he wanted to go for even much bigger one. He is Unbury bound, standing in front of the telescope. This is his which direction it is going? This is the optics. Here two detectors are there, two PMTs. And then in the lab, the correlation is going on. So then he thought of going for 2-kilometer baseline. So he found that the font is a big problem. But it was in his mind, 1974, he thought of that proposing. So meanwhile, in 70s, Levery, he found out that how to beat the atmosphere. The atmosphere normally behaves like this. If anybody has seen that even the waves in the river, it starts with a bigger one and then slowly it breaks. So the Kelvin-Helmholtz vortex, it starts breaking up and then it becomes smaller and smaller. Now, initial flow, the laminar flow, if the Reynolds parameter, if it is 1 to 100, that is the laminar flow. And if it is more than 10 to the power 6, it's called turbulence. So let me go to this. Okay. Now, look at this. Above the atmosphere, your starlight is coming as a parallel this one. In the atmosphere, there are several layers. About, say, a kilometer above, the atmospheric cells are much bigger. As it comes down to the ground level, it becomes smaller and smaller. And then there are several layers will be there. So this starlight, it becomes a turbulent one. So it is not coming straight. So one or two of them are getting interfered, sometimes 3, sometimes 4, depending on this one, wave structure. Now, if you have a telescope which is less than the size of the turbulence cell, you get a sharp peak. If you have a bigger one like this, then you are in trouble. You will get small lobes called speckle. Now, what here we have done is one of the unresolved stars, we did the Fourier transform and autocorrelation. Look at this peak. This peak is the diffraction limit of the telescope. Say this is a 2.3 meter telescope. The diffraction limit is 0.05 arc-second. That image should be like in principle this, but because of your optics structure, that wave is the air is cool air is coming down, hot air is going up, it's getting mixed up. Then there's a primary cell here. You put hand inside, you will find the temperature is higher. So then the turbulence are getting mixed up. There is a polar mount, and then you have a dome. In the building itself, Dipanko knows that. I think Olagupta also knows. There is a AC plant, ground floor. Then there is a dark room. Then there's one pantry also down. Then there is a library. There are some places are blocked. So and then we have a aluminizing chamber. So the air is hot air is getting trapped. Then slowly it starts coming up. So the cool air and hot air, it makes life miserable. And and then mirror cell also is become hot. By the time it cools down, already midnight will be going up. So once you do this is a seeing disk, half of them. It's an autocorrelated image. So it is, you take the central line and then this half is the seeing. The actual image should be half of the top thing. Now, see, with no turbulence, theta will be lambda by d. D is the diameter of the telescope. Lambda is the wavelength, which wavelength you are using it. You are better off if you use infrared because R0 size increases lambda to the power of 6 by 5. So this is optical. I calculated. If you take 0.5 micron lambda, then telescope diffraction limit is 0.05. Are you hearing? Yeah, okay. And with turbulence, that image will be between 0.5 arc second to 2 arc second. So it depends on the seeing. If it is 10 centimeter cell, then seeing will be 1 arc second. Mostly it is more than that. And so suppose if you have a closed binary star, which is separated, say 0.1 arc second or so, you will not be able to resolve it. You will declare it as a single star. Now, this is a conventional image. I call it conventional because any exposure more than 20 milliseconds is called overexposed. And the overexposed is your conventional. Whoever is giving any exposure more than 20 milliseconds is the blurred image. Now, if you go for a speckle image, look at that. This is how it behaves. See how fast it is moving and changing. And if you see carefully, one of the frames will be sharper than the other one. And it dies and forms. The lifetime is few milliseconds, depending on the seeing. If it is infrared, seeing is good, lifetime will be more than 100 milliseconds even. So you can give 100 millisecond exposure, even sometimes even 500 millisecond exposure. But if the seeing is bad, say 0.5, that the 5 centimeter size are not, then you may have to give 5 millisecond exposure or 10 millisecond exposure. This is 20 millisecond exposure, the one which I gave. Series of frames, and then I put one after the other. If you add up one by one in the image plane, then you get a blob. So this is the actual blob is coming overexposed. Same star. Now you can't say whether it is a binary or normal or that normal star. So what I did the Fourier transform and autocorrelation. There is a secondary peak here. It's actually a closed binary star. Separation is about 0.47 arc second. No. So this is the instrument which I built. Idea is to send the beam, and there is a low expansion glass to run 50. We made a pinhole in our lab. Mr. Jorajan, who was involved in 19-inch grinding machine, the telescope, who made that 19-inch mirror, he and I sat days after days, and then we made this pinhole size of 350 micron. The idea is we want only 2.5 arc second allow the image should go inside. The star, if it is more than 2.5 arc second seeing, the star will not go. It will become blurred. The seeing should be before that. So then we made a pinhole, and it is 15-degree angle. Then part of the beam will go to this particular place, and there is a converging lens, reimaging lens, and ICCD will see and declare that this is your object, and your idea is to pass that object through that particular hole. As soon as it comes here, the magnifier, it was into 10, so F13 becomes F130. You have to expand it because that each speckle, that each blob should cover 32 pixel size of your CCD detector. Otherwise, you cannot get any information. Now, there is another problem is the dispersion effect. Once the telescope moves from the zenith, the dispersion effect comes into play. So there are two ways to solve it. One is Risley prism, counterclockwise. You rotate it with the computer and then calculate. There's a very cumbersome job. The other one is a narrowband filter. So what I did is I put a narrowband filter here. Then I have an iris here so that the extraneous light cannot pass through. Then this is a scientific detector I have put. Which one? You see, the one which I used here, it was this one, frame transfer CCD. It was there. They bought it for guiding. So I used that one, which is not exactly scientific one, but I have to do some experiment because they will not give me 20 lakhs. So I think director also changed. Some other people pay. The other detector, I got it much later. So I was using that particular one. The other normal CCD cannot be used because you can't give exposure 20 milliseconds. And that too, frame has to be taken one after the other, series. You have to take about 100, depending on the magnitude. If it is fainter one, you have to take thousands of frames. If it is a normal, say, third, fourth magnitude, you can take probably 100 or 200. And not only this, double the size, the number of frames you have to take for reference star. And that reference star should be available within 1 degree of the object star, so that the atmospheric turbulence can be calculated before and after. So you have to analyze first reference star, then the object star, then divide it. I'll come to that to calculate. So this is the instrument, and then this instrument on our building, this man was sitting in front of my office, he and Sujan. Once in a week, I used to go to CMTI across the city, almost like after IASC, somewhere there. Sit with them, they had wire cut machine, computer-aided machine, which our lab did not have. And then I did some research and found stainless steel magnetized one, whose expand that, you see, the temperature changes, that these plates should not expand. So that kind of a plate we gave to them, and then they analyzed, polished it with a micro this one. They the error of those plate itself is about 5 micron maximum. And then we made this kind of structure, put it under FM analysis, and we found out that even if you put 20 kilo weight of the detector size, including the wire, etc., the flexibility came down to 0.2 micron, which is much less than the Speckle, this one. So it's very, very rigid and very strong. And those mounts, you'll be surprised. You know what we did? This is my idea. Take that entire rod, that cylinder, pipe, that not pipe, that rod itself. You cut rod with the wire cut machine and straight away make it an angle bracket. No joint, nothing. So that there will not be any tilt or flexibility. So this is how we made it. When we sent that paper to experimental astronomy, this is a beautiful instrument we have ever come across, because you require this kind of thing. So this one, this is the instrument. Anyway, let me proceed, for the other you cannot finish it. This is conventional imaging. So those, because since the number of frames are less with that frame transfer, so the idea is that with a single image, how to analyze the image processing, it is called blind iterative deconvolution. So you have to find the prime number, go down. So what I did, we made a binary structure simulated one. Then we made a phase screen, and then combined it. This is the actual frame. So this frame, if you look at it, you can't say this is the Speckle frame. Normally we get with the telescope. And then it's an iterative deconvolution technique. And then after 250 iterations, I got my binary structure. And if you look at this, the reference star, this one is almost matching. So once I made it success, I used the same star which I showed you, the binary, that I used as the input, and I gave 2 pixel size as a guess. And after 350 iterations, I got my result. This one. And same technique used by Nissenson for supernova 87A. And he did this one. And the same thing, 1994, July, there was a Shoemaker-Levy and Jupiter clash was there. I took my instrument, not this particular one, the other one, I made another one. to shoot with Rangapur Observatory. They had 1.2-meter telescope. That Nasmith focus. I went there and took Jupiter images, analyzed with this BID, and you can see those spots here. And that was the last observations with that telescope. After that, they tried to model it. It never worked. Anyway, BID. Prior information, yes. Technically, prior information is that you have to give some guess. That guess, see, here I gave 2 pixel size radius as a guess. But in this case, what I did is the reference star. The reference star, one of the images I put as a guess. Again, for Jupiter, I used a very small window as a reference, as a guess. And I got the result. Even JCB was challenging me, extended observatory, how will you do it? I said, you give me some time, let me do it. And I did it. So that is the BID. But then problem is that BID takes only 1 frame. So you can't go to the fainter one. By then, I started concentrating on the triple correlation. That is the safest algorithm, direct method. So the what you have to do is you have a frame, take a frame, and then measure, and then you shift it in one direction. Then conjugate it, so it becomes 3. Do the Fourier transform, it becomes bispectrum. And then you do the autocorrelation of that bispectrum, it becomes triple correlation. So the direct triple problem is that it takes huge space because the calculation becomes 4-dimensional. And those days we had only Spark station. Speed was so low, you submit and then go home and come back. By then some power cuts might have happened and it's gone. Then again you submit. Days after day, you have to have a huge. When I was running BAD in Kawal, it used to take hours. Then later on, of course, sophisticated instrument came down in the late 90s. Then the speed, you require less speed. So then it worked. See, next to the frame, what we did is we put again binary here. And then we put again the Speckle frame, combined it. We did the bispectrum. This is the bispectrum. So that people, if you put as I said in the first slide, that put a third hole or aperture, you are supposed to get fringes. 2 of them will, this one is there. See, you have one here and one here. These 2 will give you fringes like this, perpendicular to the aperture. Okay, you bring it some more. These 2 will give you fringes like this. And these 2 will give you fringes like this. Okay, I was supposed to get this kind of fringes, but then 2 of them gave fringes. Other one is coming very close, but it's not marching. That is why I missed. But here, similarly, when you shift the image in one direction and then conjugate it, you get a bispectrum, the triple correlation. And you see the bispectrum here. If you do the image the inverse autocorrelation, you get a structure like this. Now, it is a autocorrelated image. Autocorrelation will never give you phase information. It will give you the amplitude information. There is a first order information that yes, it is a binary. But now which direction it is? For that, you have to do a lot of the what do you call you have to make a lot of angle calculation, phase calculation this way, and then that is where it takes a lot of time. All around projections, and then I got this. Look at that structure. Both are same direction, same amplitude. So when we got it succeeded, by then it was almost late 90s. This is the Weigelton group. They did a lot of work on the direct bispectrum. See the bipolar nebula, red rectangle structure, like a exoplate. Then this is a very interesting object. I think it is R136A. One full day they spent in IU colloquium the assembly. That is it a black hole? So Weigel took his instrument, went to Hawaii in 3.6-meter telescope, the CFHT, and he found out it is not a binary, it is a multiple, because he used Speckle interferometry. It's a multiple stars very close to each other. And he found out there are, this is the initial phase. At the time he said that 8 components are there. Then later on he used a bigger telescope. He found there are 42 components are there very close to each other. So it is not a black hole. The conventional image says that no, it may be a black hole because the mass is very high. But he found out that no, he declared that it is a multiple stars. And this is another one. So this later, when our MTech student program started, MTech program started 2008. And then one of the students for this project, he joined me. Then I said, look, if you can, first you make triple correlation, normal one. So he did it. For his PhD program, I suggested that radon transform you use. You don't need to do Fourier transform. You do it on a image plane itself. It will be much faster, and you may get the result. So what he did is he did a projection-based, two-dimensional image, projection-based calculation. And you see that with this particular one, it's a simulated one. That is a real image. And one of my old images, he has used it. And with 10 projections, he got this kind of structure. With 150 projections, you see that almost the same. So it became success. And then I said, you use a normal image. So that also he got the result, I show you. He analyzed, he said 200 frames computational time, direct bispectrum with 200 by 200 pixel. It takes 1 hour, 21 minutes. In those days, whatever we have the latest computer. But tomographic code with 180 projections, it takes 15 minutes. And plus pixel also more. You can use more pixels, 10 to the power 4 to the by 10 to the power 4. So, and then if you use 18 projections with 2 minutes itself, you can get the result. And you can see that the same image he has used it. This is the bispectrum, and this is the result. So this we published it in 2014 Journal of Optics for his PhD program. And then he did some more simulation with hyper telescope. You see with the binary 4-phased image, Speckle frame, reconstructed image, then extended object if you have a spot like this, how it works. And this is the reconstructed image. Then again, there are 6 elements here, and we have reconstructed with the radon transform tomographic image. We found out this. Now let us come to other one that today morning you was talking about the adaptive optics. My idea is to talk something else again. I will tell you. I explained him. What is adaptive optics? You have to correct it online. So far, whatever I have talked, there is a passive passive method to get the diffraction limit. This is the active method. Directly, you are supposed to get online, real time. But that is offline. You get your data, come home, sit with the computer, you analyze and then get it. But there on the spot, you have to get it. Now, how do you get this? Say, for example, incoming light is coming, but then you have to have a deformable mirror. And you have to run it with the actuators, with all actuators, and then how fast you can run. There's a beam splitter wavefront sensor, and it will give you the indication that how much you can correct it, then corrected image, and this is your high resolution image. Now the question comes that how many actuators you can run. See, Keck telescope, 10 meter size, and they had only 380 actuators. They could manage. Now, optical bandwidth, even if you take, say, 10 centimeter or 20 centimeter, 10 meter divided by 20 centimeter is how much? Calculate first, and then square it. That many actuators are required for visible wavelength. Whereas infrared, you are better off. Lambda was 6 by 5. So you with 380, well, 60, whatever they are, 85, I think, or 86 or something, that actuator, that was sufficient to get the image, that corrected image. But that also, they after getting those images, they use Speckle interferometry technique to collect those data, use the best images, not all 1,000 frames will give you the best image. One of the out of 1,000, you may get only one or two, or maybe 10 maximum. Then 10 to get 10, you have to have probably 5,000, 10,000 frames. And you look at it and see sharpest one. And then shift and add, they used one after the other. That is called lucky imaging. One after the other. Add it up, and then you get the sharpest image. This is the best way to do it. And I'm not sure whether you people have seen that paper or not, 2002, Reviews of Modern Physics, which I wrote. Exactly same thing I mentioned. That combination of adaptive optics and speckle interferometry will give you better result. Individually, it may not give, because till today, visible wavelength definitely not, because your actuator is a big problem. Infrared also, you will get better one. So I'll come back to this. The people have done this experiment with the, at that time in late 90s, people have made it success. With AO off, you got this kind of blob. With AO on, you see there's a faint star here, and there's a tight component binary system. With 6 meter telescope. 6 meter telescope means there was a 1.5 meter, 6 mirrors were there. It is called MMT, multi-mirror telescope. And it failed. Then they removed all these structure, made a new one with a 6 meter telescope, replaced it. And with that, these people, they have used adaptive optics in late 90s, and they made it success. Now, in our lab, in optics lab, they bought one toy machine. Those days, probably some 12 lakhs or something, called adaptive optics system. There, again, my student, he has made a face screen. Not made, I think it was available, they bought it from somewhere. It's a collimated beam, and he has put a aperture mask there. And then he found out this is the original binary source. The binary source is here. And then if with face screen, you get this kind of image. My source is here, binary source. And then at the end of the output, you got the structure. Now, coming back to your question, one of our senior engineer, Dipankar knows, Chinnapan, he was doing his PhD. Again, I gave him the data, the detector, etc. They had a 6 by 6 element Sack-Hartmann sensor. With a aberrated one, there will be Cassegrain, no, there's a hole. So he used it, and then aberrated image he found out without Sack-Hartmann correction. Then if you put the plot like this, you get like this. With the corrected image, the sharpest one. So at that time, when Chinnapan was writing his thesis, I was correcting it, although he was not my direct student, but he was my friend. So he said, running 6 by 6 itself is a tedious job those days. Okay, so now you can calculate a 3.6 meter telescope. I was calculating how many actuators you found out. So, no, 1,300 something. So 1,300 actuators managing, and it's a huge task. Now, yeah. Now come back again, why I said that adaptive optics, this Andrea Gay and Eric Gangel, two group. Eric Gangel was working with Charles Towns with his infrared stellar interferometer. Initially, they were trying with measures. Then they used that one. But then he was not very happy because their idea was to go to the black hole, Sagittarius. So what he did is he went to 8-meter telescope, VLT. He's from German, so he had access. Although he was a professor of Boulder, Caltech, University of California, but he had access to VLT, so he got time there. So he attacked the problem for Sagittarius A star. It's an excited one because it's supposed to be the center of the galaxy. And they started observing from late 90s to 2008. Andrea Gay, who was a student when we were doing telescope interferometry in France, she just joined as a student, 88, in Caltech for doing masking. Our masking was at the top of the telescope. Their masking was at the focal point. So any minor error at the focal point will cause a lot of noise. So they started doing it. So anyway, she did her PhD there. Then she moved. I think she was one of the observers of that 6-meter telescope, the adaptive optics. Then she joined as a faculty, University of California. Then she used that Speckle technique because telescope is already fitted with adaptive optics. Shift and add, both the group, Eric Genzel as well as Andrea Gay, they used Speckle technique, shift and add, got the results, similar results. And independently, both are independent, but they are the leader of the group. And what they have done, this is the, there are so many stars are moving around that particular object, this one. And this solar mass is a 4 million solar mass, heavy object. And the closest one is that S2. S2 is given by this man, Eric Genzel, and Andrea Gay says it is SO2. So that the one round, it takes 17 years. See that? This is the star, and this is a 60 billion kilometer. That is the closest one they could identify. There must be inside, which cannot be even take that detector. They are using NICMOS with a longer wavelength. And this to 2020 Nobel Prize, along with Penrose. Penrose got 50%. The remaining 50% was divided by these two, Eric Genzel group and Andrea Gay. And that is the time editor caught me to write. So that Journal of Optics article came 2022, the article came. So I explained everything there. Anyway, so that is the story of the single aperture interferometry. This story I'm talking about because my interest in 88, when I got a chance to work with Levery, the man who is the pioneer and who discovered that technique of speckle interferometry, is Mr. that Levery, 1970. He, after doing 2-3 years, he gave that instrument to his students and they, okay, you continue. He got fascinated to have 2 telescope interferometry like radio astronomers. And then what he did, the idea is that he used 26 centimeter apertures here, normal, Nasmith focus. And then one particular star, the first star which here, the Alpha Lyra, which was just at the horizon, this one, that zenith at Nice Observatory. He has put 2 telescopes. Let me not discuss, these are all physics matter you can learn later. This is the instrument he has, one here, one here. That is the Hartman, where his central lab was here. That is the time Henbury Brown and Davis, when they were planning to go for a bigger size intensity interferometry, because they are not getting photons beyond 2.5. And as the star becomes fainter, you require longer wavelength. So that becomes a cumbersome. So for intensity interferometry, of course, there is no problem because you can take one can be here, one can be even 1 kilometer away. But the problem is the photon. So he came and visited. John Davis and Henry Brown came and met Lebery, saw the fringes like this one. Immediately he commented, "You guys have lots of signal to noise." Then he dropped the idea of going further with intensity interferometry. They stopped. Now, after making this success, he moved to, there's a place called Observatory de Calan, and it's 50 kilometers from Nice Observatory. There's a mountain, and he is the man, he's a Lebery in those days, his age. He was probably at the time mid-30s or so. And but this is the telescope. Once that got succeeded, that the smaller one, he became ambitious to build the interferometer with 1.5 meter diameter. And he made this kind of a jar. This is the bowl telescope, used to call the jar. The primary mirror is sitting down, secondary mirror is here, that, and then tertiary mirror send the beam to the central lab. Central lab is somewhere there, not this. This is his workshop to make nut bolt, etc. And that is the place both the beams used to come. And this is the principle is like this. The collimated beam comes, the achromat, 70 mm achromat, and then both the telescope, this is a beam combiner, then the beam here. Here, that it is a translation, it can be shifted up and down. So without this, the beam used to come here. Then you observe, see the fringes. And the fringes, it's like a flexor. You have to, you can see, but it's very fast, it get vanished. Then another one comes. And then as soon as you see the beam, he pushed this prism here. The beam goes to the grating, and then CP40, that is 40 mm photon counting system, which he has developed it in his lab with his engineers. Everything was done by them. And then you record it. So this particular paper, when we published gamma gas, we used to manually shift those baselines. First, you make it very close, see the quality of the fringes, then slowly you shift it. So with 22-meter baseline, we could resolve that particular object. And you'll be surprised, we took 300,000 frames in 5 days, continuously. And you can't observe more than 2 hours because the star is moving. So if the star goes in a particular direction, it will have again dispersion effect. So per day 2 hours, 5 days continuously, with CP40, which was taking 50 frames per second, we collected 300,000 frames, and we analyzed it, and that is the paper came in Nature. That was the first result of that interferometer. This is the kind of fringes. Look at that here. This is the type of fringe. So you can add that. Then once you do the autocorrelation, you get the sharpest. So each baseline you calculate, see the strength, go to the next, and the temperature was -12 degrees. And we used to go out, push the telescope, put this one, lock it, and then come back to the lab and watch, and then do it. So many terrible patients were. And this is the combiner. That was a project given to one of the students, got a PhD on this. This is the CP40 instrument. Those are the two achromat. Beam used to come, combiner, and we used to watch fringes here. As soon as we see, then push it. So that is the original instrument. After it got succeeded, throughout the world, everybody got interested to do interferometry. And after that, about a dozen interferometers came. Look at that. This is the Sydney University, that same Davis group, that Hanbirborn Bajan retired and left the place. But Davis continued. And then they made this kind of stat. Then this is the Keck telescope interferometer. This is the VLTI interferometer. This is the binocular telescope. That is the same structure. The two mirrors will be there, so that it will not have any this one. That you don't need to sheep or something. You can have that it will move. It will follow the star together like a normal telescope, but the mirrors are different. And see how many people are continued. Now, of course, this is running. VLTI is running. LBT is running. ISI also is running. Most of the others, they wound up because the limitation, there is a limitation, then how much you can go faint. And you can see the Myra variable, which is bulging and shrinking and bulging. And they measured that 1997, they got this milliarc second diameter. And then again, 1996, they got 28. So it is shifting, these spatial frequencies increasing. So the Myra variable type, then one of the conferences, one senior professor, ex-IIT director, did a lot of work in optics. He asked me, did you see any changes? I said, if it is Myra variable, you'll see. If it is a star-like sun, you have to wait for a million years. You see, once it becomes a supergiant or giant, that is the time you will be able to see. People started laughing. So I said, look, without knowing subject, you don't ask any foolish question, which will make you a fool. But see, Myra variable, everybody knows that that very fact is a very old star. So we can, anyway, we did some plotting that binary orbit. Like Andrea Gay and Gandel did the orbital calculation. We did based on Jacobian matrix we used and least square method. That I mentioned details in my book, the first one, also that 2007. How do you calculate this? And these are all interferometric data. Again, we between 61 to 70, there is no interferometric data. After 70, that Speckle interferometric data came. Then the multi-telescope interferometric data came. So say 18 stars, but you can see there are a lot of errors. And the top left 36 interferometric data, 75 to 2000, see the very sharp. It is following exactly the oblique, the binary structure. So then the latest concept now came hypertelescope. That is, you have a spherical structure with a mountain edge somewhere, put the mirrors scattered away. It can be small, 200 small mirrors or even more. And then you can have a correction. The beam will come, a mass corrector, because spherical mirror will have errors. So that can be corrected only by mass corrector. Then you densify the beam, you get a sharp. So if the normal piezo mask will give you this kind of structure, but if you densify it, you get a sharp image. So these experiments are going on now in Levery. He's doing it. So I'm not sure when he's going to be succeeded. He's already close to probably 84, 85. And some of his co-workers are working. I think Orun also went there and worked for some time. Okay, I'm also. So this is the hypertelescope first one. He found out some result, one particular star. And then again, Orun did some kind of analysis with a radiative transfer code. So if you have a 96 elements and if you organize them like this, then UV coverage you get this way. And then if the AGN in the polar mount and the edge on, polar on and edge on, you get this kind of structure. Then he used a extended object like exosolar planet type of thing. And then if it is a 400 nanometer, you get this kind of structure. 660 nanometer, you get this. And you can resolve it if any exosolar planet is there. If it is the parent one, this is the one. Of course, now people are even doing the revival of intensity interferometry with multi-telescopes. Some work is going on. I saw 2020 some papers, laboratory experiment, we got some results. And whatever I talked, everything will be mentioned here. The first one talks about the single aperture interferometry. Second one talks about multi-telescope interferometry. This is the one talks about the what kind of detectors are required to attack this. And this is a basic one, the last one, waves and oscillations. So that talks about the basic waves to alpha waves, everything, all those mathematical calculations, they're basically theoretical one. So this, of course, we both, actually Satanara got the offer. He came to my room. I said, I have got 80 pages, write up, you take it and do whatever you like. Then he comes to me, no, I'm writing your name also. I said that I cannot start now. I can start only after I finish my third book. He said, no problem, I will wait. So that is the thing. This is, and the last but not the least one, I'm now writing on fifth book. Basically, it's a basic instrumentation. It will have spectroscopy, telescope, microscopy, medical imaging. The book name itself is Paradigm of Optical Imaging. So earlier I thought I can finish it in 200 pages. Now I find even 700 pages it already crossed. References came probably 18 or 90, maybe 20 pages already it is there. And indexes also, it probably had gone more than 15, 20 pages. So I may require another couple of months or two, probably 3-4 months to finish it and take some break for some time. So that ends my talk. If you have any question, you can. And I'm available even tomorrow also. I'm sitting near, adjacent to his room. If anybody is interested, they can come.
Okay, questions?
While you do the image reconstruction, like you showed, so you give some like frame from the reference, or you give some guess value.
That is a blind iterative convolution.
Okay.
Not for triple correlation.
Okay.
Triple correlation, you have to give only the actual data.
Yeah. So suppose, so how sensitive your final result is, or how unique is your solution? Like after you do the analysis, so how
Triple correlation is the safest algorithm.
Okay.
That first you are doing it autocorrelation.
Yeah.
Autocorrelation itself will give you that it's a binary structure or multiple structure. Okay, but you will not be able to calculate the phase. And there you have to do the phase angle, you have to create one by one and then see the weightage is which side. So it will automatically come, after calculation, it will come the weightage. So this is the binary structure, phase is this information. So triple correlation will give you phase. So this one, it will give you the phase information. If you have more number of apertures, you will get more better. Okay, but the two telescope, it will give only the amplitude information. You will not get phase information because it is lost. Once you do the autocorrelation, the phase information is lost. Like two telescope interferometry. Two telescope interferometry will give you amplitude information. You can say that yes, it is resolved at this particular baseline. Okay, and you can calculate that how many arc second it is. But to get the phase information of that particular one, the one which you have resolved it, then you require more number of telescopes. The number of telescope, if it is more, you get better accuracy and you can calculate. The 3 is the minimum you require. That is why the Jennison, when he left that the Henry Brown, he tried to analyze, he continued that intensity interferometer with putting a third one. And then he calculated the 1957 paper. You can see that. Jennison, he said that with 3, that phase calculation will be here.
Okay, for the
Just general question, why speckle imaging is not very widely used in most of these
It
telescopes?
depends on the person's interest, number one. Number two is the detector limitation.
Because nowadays, I mean,
How do you say that? Even Andrea Gay and those people got old by using speckle technique.
yeah, that's why I'm saying it's a
But the
powerful
telescopes did.
yeah. Cameras now with yeah.
You have to freeze the atmosphere turbulence.
Nowadays there are very fast cameras, even 1 kilo.
Yeah, but then again, the problem is that how faint you can go with the present day of photon
Yeah,
counting
that is
system.
true.
That is one thing, because most of the things, whatever is available, these guys have already done it. Say, for example, this is a 20th magnitude, I think that the Sagittarius say, and they could observe because it is adaptive optics fitted instrument was. So once it is ready, the finer corrections so they gave with this speckle technique, the combination of both, the single telescope. Again, with multi-telescope problem is that again, you cannot go beyond 6 or 7 magnitude because photon becomes less. As you go beyond and beyond, number of photons are coming down. So your detector may not accept it. Again, another problem was that same detector, suppose in the two stars, one is the difference between two magnitude difference, the fainter will not detect. The brighter will detect. So it should be within two. There's a lot of limitations of it.
And also you have to observe near zenith mostly.
No.
It's not.
You can go up to 40, 45 with interferometry, the interference filter. If you use Risley prism, you can go up to 60 degrees. Beyond that, the atmospheric dispersion effect. So what I did is that because handling Risley prism was a very difficult one. You have to anti-clockwise, that one will move this way, other one will move this way, and then you analyze it with the computer and then see how it goes. I said, no, we'll go for interference filter, 50 angstrom bandwidth. And pardon? Yeah, but I didn't use it. My problem again that handling computer even with the Risley prism will become a very, very cumbersome thing. But again, if you put 50 angstrom bandwidth, your photons are coming less. So I could go up to 5th or 6th magnitude, the kind of detector which I had. There is a latest one I heard Peltier cooled photon counting system that which those people have brought out. That is not sufficient unless you put another intensifier there. Then the dissaturation comes into play. And by then, of course, I got involved with some other thing. People started inviting me to write something one by one, including that reviews of modern physics article. That editor wrote to me that after I published the 106 pages in bulletin article, one of the editors saw that and they immediately after me. And that took 2 years to write that article. Reviews of modern physics. So it became channel. Once that got published, normal publisher started writing one after the other. Write one for us, write one. So I could not say no. Even now I have got a couple of invitations, but I have not given any word because I'm also aging and I have to find some topic also. That was 2000, 1st January, I think 1919, December end and January 1st. January 1st, I gave a talk here. Yeah. Vijay Mohan, Ramsagar, then Mahendra Singh, those people are there.
Okay, if there are no further questions, let us thank Professor Saha again.
Thank you.
Yeah, just one story about Professor Saha. We were all in the 4th floor. I still remember Shapunda had his room, all this black sheet paper.
Because I did the experiment in my room. I was not even given any lab.
I actually 4th floor, if you go, all the rooms had a provision for developing thing. The first time I joined as a student, I found the office I've given has a sink with water supply and a slab, and then some cupboards and other. What do I do here? Then I found out everybody has this. So all astronomers is supposed to develop their own
Tea, coffee.
And tea, coffee, whatever you want to in the room. Don't go. But he was so nostalgic, he didn't remove the black sheet of paper until he retired. So once he
No,
retired,
even now it is there. I recently I went.
ah,
I saw-
no, people will say, yeah, this room will be now
No, not,
lighted.
not sheet paper, not a sheet of paper. I blackened the
You
entire.
blackened the
And
glass itself.
Because I had to do experiment
Yeah,
at
yeah, yeah.
my lab, that room.
So he was always staying in his dark room. So and of course, he was the BGS chair. So we
That is
were
later.
afraid of things. Later on, when these people were students.
And he knows that my timing also got changed because I used to go at 7 o'clock. See, the kind of, I think I didn't mention that. See, when we could not get the fringes, the third one, then what was wrong? Let me try in the lab. So the lab, we started simulated the artificial telescope with the phase screen. That phase screen was developed again by ourselves. See, the Levery's initial experiment, he did the phase screen by putting silicon oil. But then silicon oil, you don't have any control there. You don't know how many centimeter or millimeter size of the cells. We said that you will calculate that if the lens size is this, we will make it say 5 millimeter or no, very, very small, 2 millimeter or 1 millimeter, depending on this thing. We made a lot of phase screens like this. And then we got the speckles. And then we put the 3 aperture, 4 apertures and see. We got absolutely fantastic fringes. But then with the photographic film, some of them used to get masked. Then we discovered that he knows that the opposite library adjacent to Rajmohan room, we had one dark room. And then he used to, the moment SC plant was just adjacent, those separate building,